All right, so your equation for this, I move this, it's going to bop me back, and then I can get over to here, and then I can move it again. There we go. Okay. So the equation for this unit typically is going to be M1V1 times the moles equals the moles times the molarity times the volume. Okay. So they're all going to equal each other for this as far as your first data set and your second data set to get to a neutralization. So if you're doing a neutralization reaction, this equation will get you there. And I think that's written in your, yeah, it's all right there. If you don't want to rewrite it. If you want to rewrite it, go ahead. All right. You're going to be doing a titration for this unit when we get into something called a redox reaction. And it's not actually an acid-base titration. It's going to be a redox titration. But you've done this titration before where you did the you guys did a strong acid, strong base titration in chemistry. Okay, back in the day, maybe. You used one of these guys. Remember ever using one of these? Okay. So this is a burette. Okay. All right. So it is a analytical technique where you have a known volume and molarity of your titrant. That's the stuff that's coming in from your burette. It's going into a flask, and typically that's going to have, they'll have something called an analyte, which is what you are analyzing, okay, to try to figure out what's going on, okay? And typically with that analyte, you're trying to figure out the molarity of it or the moles of that material that's in there. For you, it's going to be, I believe, the moles of iron in yours that you are looking at. Okay, you're going to use a balanced equation, and you'll be able to figure out moles of titrant and where that equivalence point is. For you, the equivalence point is going to be a color change. It's not going to be a bright red color or bright pink color change like it was in chemistry. It's going to go from clear to like a kind of magenta color. Okay. Later this year, we will use titration when we get into our acid and base equilibrium. And with that, we don't actually use a color change. We use a pH meter to be able to determine where that end point was. So you have a pH meter in the stuff that you're analyzing, and it's plotting that change in pH as you go along. And then you go back and you determine your end point from your data. You actually use a second derivative to do that. But the computer calculates the derivative, not you. So you don't actually need calculus for it. Redox titration, you don't know what redox is yet, but you will. And that is the titration that you're going to be doing. And then we also have precipitation reactions where they're going to form a precipitation in the process. I haven't seen one of these precipitation reaction titrations on the exam before, but it may happen. I don't know. Anyway. When you are doing these, the equipment needed, burette for keeping track of your titrant volumes. Oh, and by the way, if you ever have an option between using a burette to dispense volume of something and a janky graduated cylinder, always go for the burette, okay? because the burette is much more accurate than, so always use the most precise piece of glassware you can for measuring. If they give you a listing of it, okay, they give you a listing between a beaker, a graduated cylinder, and a burette, what do you go with? Your burette, okay? If they give you a burette or a volumetric pipette, go with the volumetric pipette, okay? Because the volumetric pipette is even more accurate than this. It's skinnier, okay? It has much more accurate, but it's only for one volume. That's the problem with those, is typically they're only for one volume. These can get a whole range of volumes out of them for the burettes, okay? But I got a lot of you. I got most of you on the test last time because you chose to use a graduated cylinder instead of using a burette. Okay, if you're always choose the most precise piece of glassware you can to get your volume measurements if given an option. Now for the lab, you weren't given an option. You were only given a graduated cylinder. Okay, but in that listing on your test, you were also given a burette. Guess what you should have picked? Burette. Guess who lost points because they didn't choose burette? And I had mentioned that in lab or in lecture. I made sure to mention that, but it must have went over many of your heads. So hopefully you've got it pounded in there now for the May test. And that is why we do corrections. Okay, volumetric pipette for dispensing specific volumes of the analyte solution. I had you do that when you did your acid base lab. I had you use pipette to be able to get out the right amount of acid into the beaker. Lab balance, you're going to have to use that this time for this redox reaction. You need an Erlenmeyer flask, which is what's going to contain that analyte. And then an acid base indicator or some sort of indicator that's going to tell you that the color change has happened. And or a pH meter, which is what we'll use in the spring when we do this lab. Okay. You need to make sure that you're recording the molarity of the titrant. So the stuff that's going into your burette, make sure you record that. The initial volume. It doesn't matter what the initial volume is as long as you've got that recorded. So you don't have to be exactly at 0 on here when you start, okay? But you've got to at least record where you're at, okay? And then the volume or mass, and it's going to be mass for this lab that we're doing to this week or next, whenever we do that lab, the mass of that analyte, which is in your flask, it's what you are analyzing. Okay. Now, the thing about these burettes is, remember, they're backwards. Okay. So whereas you're used to your graduated cylinders having the big number at the top and the little number at the bottom, these are backwards. They're starting at 0 at the top when the thing's completely full. And then as you drain, the number is increasing. If you start exactly at 0, then that means that however much you've drained out, when you end up at that value, that's going to be what you record. But you have to be careful because you're thinking that, oh, this is like 12.9. It's not. This is 11.1. Okay. This would be 12.9, would be down here. Okay. So it's completely flipped around on you. So you've got to be very careful. Additionally, if you put something dark, a dark background behind here, it makes it a little bit easier to read. So either your hand, typically I will have a sheet that has a black line through it, and it makes it easier because you've got stuff in the background that just kind of interferes with your eyes. The other thing is you have to be eye level with this. And for people like Andrew who are really tall, that's easy. For those of us who aren't, we've got to climb. And typically for me, I'll take one of these stools and I'm going to put my feet on the rungs of the stool, okay, on each side, and that'll get me up to where I need to be, okay? But you've got to be eye level with this stuff because it is because it is so narrow, just a little bit of difference is going to make a big difference in your answers. Okay, so you're like, good enough. No, not for this lab. It's not good enough. You're going to end up with a lot of percent error if you're good enough-ing it. Okay. All right. As far as pH meter, this is the one that we use in the spring. What you look for is where this big jump happens here. And for you, this is going to happen, and you're going to do a derivative here. So you're going to do a line through here, and then you're going to see where that crosses over. Okay? And your computer will actually tell you by doing that second derivative what that endpoint was. So it makes it a lot easier. That'll be in the spring, so that's a ways off. Okay? So again, by dropping that vertical line down, it tells you the volume that you've used. And then from that, if you know the molarity, you can figure out what the value is. So, okay. A little cheat sheet over here. How many people have not ever used a burette before? Did it? Chase, you used one? Okay. Everything got messed up with COVID, and so I'm still like kind of like, what did we cover pre-COVID? What did we cover post-COVID? You know, all of that stuff. I'm still kind of off on that. All right, so let's see what's going on here. We have hydrochloric acid. We had 10 mils of hydrochloric here. And we're putting that in our Erlenmeyer flask. They used a volumetric pipette, okay? Volumetric pipette, again, is going to be more accurate than an actual burette, okay? So if you're given the option between the volumetric and the burette, go with the volumetric, okay? 25 mils of water were added to the flask and 3 drops of phenolphthalein. Okay. We then took 0.4 molar sodium hydroxide. It was poured into a burette. This was my initial reading. And they added it in until that pink color briefly appeared and then disappeared. The NaOH was then added drop by drop until it lingered for 30 seconds. Remember, that was that sweet spot that you were all trying to get to in that lab. Remember that very faint pink, and you celebrated it, everything. And that was your final volume. They want us to find the molarity then. Okay, so first of all, we're going to find out the volume that we used for our base. Okay, so our base here, we would have 18.50 minus 0.51, and we end up with 17.99 milliliters. And that was OH minus. Now, I want to find out the moles of OH here. So what am I going to do? What do I know about my base? What other number have I not used yet for my base?
Is the molars.
The molarity, yep. So I've got 0.4 molar. That equals moles over volume. But I have to convert this into what? Liters. I have to have, anytime I'm dealing with this molarity and trying to get moles out of it or trying to get volume out of it, I have to have that in liters. So that's going to be 0.01799 liters, which means my moles of OH minus are going to equal okay. So if we look at our balanced equation, which was NaOH plus HCl, what are we forming? It's a neutralization reaction. What's neutral?
NaCl and H2O.
Right. So we're going to form salt water, essentially. Okay. If we wanted to just look at a net ionic for this, what would be our net ionic for this? What do you know about sodium chloride? It's aqueous. Okay. So that guy and all of its components from this side are going to go out. So that's going to leave us with OH minus plus H plus is going to yield H2O. There's my net ionic equation for this. Okay. We talked about net ionics last week. This is balanced. Okay. So that means for every 0.01779 moles of OH, I'm going to have how many moles of H plus? What ratio are they in? 1 to 1. So for every 1 mole of this, I'm going to have 1 mole of this. So that means that I've got this many moles of H plus. They wanted to know then what the molarity was. What is molarity equal to? What's the volume for molarity? Moles over liters, yes. Okay, so anytime you have moles over liters, you have molarity. And they are asking about the final volume. And okay, it was red. Do they even ask us a question here? Okay, somewhere it says in there, huh? Oh, at the very bottom. Okay, and this is the original. In case you want to add that in. So how many mils of that original hydrochloric did I have? 10. How many liters did I have? 0.01. So there's my molarity. How does that work? Does that work? It doesn't seem right, does it?
That's not.
Oh, I know. It's because of sig figs. So if you put it in your calculator, it comes out to 0.1779. How does that? Oh, can I just not write things down? I didn't write it down right. Zero. Wow. Good grief. Okay. Just stop. Don't be mean. Don't be mean. Don't be mean. You're being mean.
Okay, I'm sorry.
I'm feeling like you're being mean to me.
Yeah, Derek's over here talking bad about you a little bit.
Yeah.
Moving around so bad, look, he sucks.
Okay. It's Monday.
Happy Monday, Libby.
As Haley always reminds me, it's Monday.
Happy Monday, Libby.
Thank you. Happy Monday. 0, 7, 1, 9, 6.
Wait, what?
That's a lot of questions.
So we're just like,
No.
There we go. And then I need to have my sig figs.
She
messed up the ball a little bit.
What did I do now, Maddie?
I think there needs to be another 0 on the front. Because isn't like the molar.
Here?
Oh wait, there.
Just stop whispering about me. It's just me.
It's just me.
Never mind, I did the other thing wrong.
Okay, I think I've got it right. Oh, God, you guys are mean.
We're not mean. We just like to keep you in line.
I know, and I need to be. All right, how many sig figs? No.
3.
Seven.
No. No. So remember your sig fig rules. Okay. Remember your sig fig rules. When you're subtracting these things, subtraction goes by place values. Okay. So this is the correct number of sig figs so far. Okay. Now I got lazy with this, and I should have done that guy. Okay. So when I do this calculation, this is going to take me to 3 sig figs. So 3 sig figs, 3 sig figs. Remember, wait until the very end to do your sig figs. Okay. Now here, this is 4 sig figs. So when I go over here, I should actually have that if you really want to get pedantic. Okay. So then that's going to take me to that to give me my 3 sig figs. So this is the correct answer based on sig figs. Darn sig figs. I think you have it right every time, and then I knock it around. Chemistry. We do, y'all. We do. You ready? Maddie, you ready? Huh?
Yeah.
Okay. All right, we have hydrogen peroxide. And it is going to react with potassium permanganate in an acidic solution. This is a redox reaction. They're just giving you that information. Okay, so there's the balanced equation. They're not making you do that. Trust me, you don't want to balance redox reactions in acid or base situations. Just trust me on this one. When you get into college, they'll let you do that. All right, so we want to try to figure out how much hydrogen peroxide was in the sample. We used 1 ml of hydrogen peroxide, and that required 15.1 mils of 0.025 molar potassium permanganate. Okay. So we are going to figure out the moles of the potassium permanganate. That's the first step. Okay. So I'm going to take my my potassium permanganate. I have my molarity here. If I multiply my molarity by my liters, that's going to give me moles, right? So molarity times volume equals moles. I just rearranged my molarity equation to solve for moles. Okay, so I'm going to take I'm going to try to take 0.0250 molar. I'm going to multiply that by what? Yep, 0.01510 liters. And that's going to give me my moles of potassium permanganate. Let's see if I can copy these down right. So that's going to be 3.775 times 10 to the minus 4 moles of K, and it would actually be just the MnO2 minus, or no, O4, sorry. All right. Now, I'm going to use dimensional analysis, or mole ratio, however you want to think about it. Okay. I know for every 2 moles of MnO4 minus, I have how many moles of hydrogen peroxide? 5. Yep. 2, 5. And they wanted to know grams. I've got it into moles right now. So if I want to get rid of moles of H2O2 and go to grams of H2O2, can I do that? Yeah, because I know for every one of these, I have 34.0 grams of hydrogen peroxide. That is 2 oxygens. 16 times 2 is 32, and 2 hydrogens, 1 each. That's how I got the 34. It's the molar mass of hydrogen peroxide. And if I can copy values down off of my notebook correctly, I can get that from my values. Okay. Titrations.